Thanks for coming, especially those of you who had to suffer through the rain. And thanks to Peter and Mike and the Newton Institute for inviting me. It's good fun to be here. So I'm going to tell you today about a large-scale pattern recognition problem that we tackled. It's a kind of slightly unusual talk, maybe from the perspective of the statistical focus of the workshop. It's a talk in which the estimation part of the problem is sort of trivial. There's essentially no learning. The model is a model that's really strongly known from the physics of the problem, and all the action is in inference. So imagine a situation where I gave you a model that you really strongly believed, and you just wanted to find the mode of the posterior in inference, but finding that mode is really, really hard. And so it's kind of a mix of computer science and pattern recognition, and a little bit about how we can do that. So this is joint work with some astronomers at New York University and two really amazing graduate students, Dustin and Keir, at the University of Toronto. And it's a project that I've been working on for a while. And the sort of the vision is to organize all of the astronomical data. And so the idea here would be, let's take every photo of the sky ever taken, all of the professional images, past and present and future, and all of the amateur images and all of the historical plates that are being scanned and everything. And let's just sort of unify them into a single database. And that sounds maybe like a data integration problem. It sounds like, well, we should just write some really big Python scripts. But if you're talking about amateur data, the amateurs don't have the ability to correctly tag their images with all of the information that you need with the precise coordinates. So, yeah. This is not part of the virtual observatory, although we are registered as a VO data provider. So the way the virtual observatory works is anyone who wants can register to submit feeds. And so people who submit data to our system, if they check a specific box, we can actually feed that data into the VO. So, whoops, now something funny has happened. Okay, so because we want to include all these amateur photos and historical plate archives and maybe satellite images that don't have very accurate positioning information, the question is, how are we going to do this? And the answer is, we're just going to solve a really big inference problem. So here's the idea for the talk. Start with just the pixels. So I give you an image, and all you get to see are the pixels. That's all you get to see there. And from the pixels, infer everything you need to know. Infer the scale of the plate, so how many pixels per arc second, the location of the image on the sky, something about the band pass, the date, the telescope model, everything. So essentially you're doing a massive inversion, a huge inference problem just starting from the pixels. Okay, so for example, we take this image and we might want to end up saying it's 7 arc minutes on this side. It contains this NGC object, and it was taken in 1964. And in fact, our system can start with that image, this image here, and do all of these things. And I'll show you that later. So maybe you think I'm joking, but actually I'm totally, totally serious. This is like, you should think of this as a sort of scary, evil plan, right? We want to suck all of the pixels of the sky together. So maybe in a domain where you're more familiar in the terrestrial domain, you might be able to sort of believe how we can do this. So here's some pixels, and I want you to infer some things about this image, right? So where on Earth is this? Where's the camera pointing? Okay, that you can do an excellent job of telling me. What are the properties of the camera? Okay, well, it's black and white. It's about 50 millimeter lens, etc. What's the date? You can tell me the date, right? There's a road going through the Eiffel Tower. That was only true up until maybe the 60s, and so things move in the world. Okay, so this is a bit of a cheap example because it's such a familiar landmark. But the idea is that if you know a lot about what is in the environment and you know how things change in the environment, then just from the pixels you should be able to infer a lot about what's going on. So it's just inference. So here's a picture of the sky. It's actually very dim. You guys can't probably see the dots there. That might be a problem later, but anyway. And then I tell you where it came from. Okay, so how are we going to do this? The idea is the first thing we're going to do is we're going to build a model which is kind of a cartoon. It's a cartoon generative model of how pictures of the sky get made, but it's going to be good enough that inference in the model is extremely informative. So here's the cartoon. You start with a catalog of stars in the sky. So astronomers have enormous lists of stars. The one we used, I'll tell you about in a second, has about 1 billion objects. And so for each object, it tells you where on the sky it is. It tells you something about the brightness and the redshift, and we don't actually use that information. Just think of it as a huge sheet. Unroll the sky in cylindrical coordinates into a sheet, and just think of it as a huge sheet where I tell you the location of 1 billion dots. Okay? And so then we come with a new image, and we want to know where is this image on the sheet. That's the inference problem, or the hardest part of the inference problem that we have to solve. So the rules of the game are sort of like this. We can spend as much time as we want building the model, but inference should be fast. Okay? So I don't mind if it takes, days or weeks to build whatever fancy data structures or inference engine you need. But at inference time, I want it to be fast. And what are the challenges? The challenges, of course, are the sky is big. The inference problem is large in scale. And both the catalogs and the pictures are kind of noisy. So just to get everyone warmed up, here's an example which is about 1 million times easier in scale than the examples we want to solve. So here's the catalog, okay? And I'll tell you the generative model that I used. The generative model that I used is there's no scaling. I just clipped out some part of this catalog and rotated it and translated it and put it over there. And then I added a few extra dots and I subtracted a few extra dots. Okay. So maybe some people are finding it. If you do find it, you've probably used some technique which is based on finding little patterns of structure. So for example, you might have seen these 3 stars here, and you might notice that they look surprisingly like those 3 stars there, and then you might sort of try and build up further evidence based on that. Okay? So this is exactly the problem. It's just a large-scale pattern matching problem. Okay, so in our problem, the catalog that we started with is called USNO, the U.S. Naval Observatory. They built a large catalog from scans of glass plates taken at Palomar Observatory. And so it has about 1 billion objects. Those objects are both stars and galaxies. Most of them are stars, but some of them are galaxies. And it fills basically the whole sky. And then there's a subset of very, very bright objects from a different catalog which we added in. So you can think of it as essentially an all-sky covering of just lists of positions of the stars. Okay. So other than the scale, there's another major challenge, which is that query images will contain some extra stars that are not in your catalog. So I've shown these here as green dots. And they'll also have some catalog stars which sort of should be there if you just believe the catalog, but are missing. And that's because your image might be taken at significantly less dynamic range than your catalog, for example. There might be stars that are too dim to see in your image that you can easily see in your catalog. Or it might be in a different bandpass. There might be your image might be in the ultraviolet, and your catalog might not have stars in the deep ultraviolet. So there might be some extra stars that you see in your image. Okay? So we call these distractors and dropouts. The extra stars that appear are distractors, and the stars that should be there that aren't, we call them dropouts. And that means that just naive matching techniques, the sort of classic geometric hashing techniques, which rely on the point pattern being exactly the same, aren't going to work. So you need to have some way of figuring out, even in the presence of these kind of drop-ins and dropouts, where the image is. So here is the model that we're going to propose. So this is a very simple generative model of how images get made. And so theta are the parameters which denote everything about the viewing. the image scale, its aspect ratio, where you were pointing the telescope on the sky, what rotation you had, and so on. And the idea is that what we do is we take all of the objects I from our catalog that ought to be in the frame of the image. And for each one of them, we convolve it with some point spread function. That's what this F denotes. So it's a delta function, and then it gets convolved with some sort of blurring function, and that produces a bump of ink in the image. Okay? So that sum there is over all the objects I, but as I told you, some objects that should be there don't appear. So we'll put a random variable z. Z are IID kind of Bernoulli variables, which say whether that star, which in principle could appear according to the geometry, actually did appear or not. So if z is 1, the star is there, but there's also a bunch of objects, z is 0, where we don't see them in the image, okay? So that's the first part of the model. And we assume that the delta function, the PSF center, is at the transformed position of the star according to the catalog plus some noise. In other words, your catalog might think that this particular star, according to the viewing parameters theta, should end up here in your image, but it might be slightly off in your image. And that's okay too. And then we're also going to add these extra dollops of ink. So J now indexes over these extra stars, these blobs that appear in your image that your catalog doesn't know anything about. And you can say that the number of these might be, say, Poisson distributed or geometric distributed. It doesn't really make that big a difference. But. So this is a simple generative model. First, I take the stars that should be there, and I turn some of them off. And then I take some extra stars, and these extra stars are uniformly at random, just thrown uniformly in the image. And then I convolve all these things with some point spread function, and I could have a different point spread function f for the extra ones than for the real ones if we wanted to make it more sophisticated. So is that clear? Everyone clear on what the generative model is here? Okay, so it's a very simple model. It doesn't include anything about brightness. Oh, it's this is very yeah. Oh, now of course it's very eager to blank the screen. Okay. So it's a very simple generative model. It doesn't include anything about brightness. It doesn't include anything about bandpass. We can add on the end of this some distortion model if we want. So we can say after that there's a sort of radial distortion term for the lens where there's some focus of the lens and things get skewed to the outside. And, but for now, let's just think of this very, very simple model. Okay, so all of the action, as I told you, is in approximating the posterior. So I'll take you through 3 approximations that we make and then give you a little bit of a sense of how we build it from the computer science point of view. So the first approximation is to assume that we can pre-process the image, estimate the point spread function, and identify some source locations and work only with those. So we take this image and we pre-process it. Actually, is there a way to turn off these lights here? I don't know if, oh, magic. No, that's it. Yeah, thank you. That might help you see them a little bit. So we take the image, we run a very simple computer vision algorithm that detects these stars, and then we actually throw away the image, and the entire algorithm operates just on the location of these red circles. Okay? So that's like saying that once you know the location of these red circles, everything else about the image you could infer directly from that. Or to think about it a different way, if we imagine a decoupling between the parameters of the generative model, there's sort of the parameters that have to do with the details of the ink, like the point spread function and any kind of nonlinear saturation and the intensity and that kind of thing. And conditioned on the positions of the sources, that posterior is very, very peaked. So the first thing we do is we just run this pre-processing, we extract the sources, and then we throw away the actual image for the purposes of finding where it is. Now, when we get back to trying to estimate everything else about the image, like its bandpass or whatever, of course, we'll return to the ink.
Is this sort of similar, I mean, the techniques, say, in match parts of the brain, scans and so on. You locate some landmarks.
Right, definitely. This is very similar to that. So the idea here is that these are spatial landmarks whose location is very informative about the overall geometry. So from a computer vision point of view, this is like an embarrassingly easy problem, right? It's everything is viewed at infinity and is essentially planar, okay? There's no, everything is rigid. There's no deformation. To a first approximation, all the stars we see from the Earth don't change their relative positions. Feature detection is trivial because all the input images are white dots on a black background, okay? And all possible realizations are known to you beforehand because I just give you an oracular catalog which tells you where everything is, right? So computer vision person would say this problem is trivial. But it has the appealing property that it actually works. As opposed to harder problems in computer vision, which don't have that property. So I'm not trying to say that this is much, much easier than, say, brain mapping or recognizing general deformable objects or anything like that. Okay, so this is the first approximation. The second approximation is that we're going to discretize our set of hypotheses, theta, about the viewing of the image. We're going to instead consider sets of matchings, discrete matchings, between image sources and catalog stars. So instead of thinking of theta as a continuous explanation of the image, which says, oh, the image is 7.6 arc minutes wide, and it's centered at RA and dec this, and the rotation is this. Instead, consider it just a discrete set of hypotheses, which an example of which might be the following. This red circle, which corresponds to an object in the image, is star number 800,000 in the catalog. This red circle is something that isn't in the catalog. This red circle is star number 45, and so on. So for each source in the image, you say either that it's not in the catalog, it's explained by the J sum in your generative model, or that it is in the catalog with Z equals 1, and then you say which star it is, or that it is in the catalog with Z equals 0. So for example, this is a green, so here red are the sources from the image, the query, and green is the catalog. So here's a catalog star which should be in the image, but which our source extractor didn't find. Now you can see very well, or I can at least this close, that there's actually some ink there. So if we had a better computer vision algorithm, it probably should have put a red circle there, but it doesn't matter. We can still explain it in the generative model by saying it got turned off. So is this new hypothesis space clear? Just a set of matchings. You just say for every red circle, which is all your algorithm knows about the image, you say whether it corresponds to a catalog star, and if so, which, or not. So now it's a discrete set of a huge combinatorial discrete set of matchings, but a discrete set nonetheless.
A few questions about your model.
Yeah, let's go back.
For example, the distortion of the location of a star, the sigma squared.
Yeah.
Is it reasonable that it is independent of the location, of the distance from the Earth? I mean.
Okay, there's a very small number of stars which have high proper motion, meaning their perceived position in the sky moves a lot, but those stars are very few in number. So, yeah. Remember what I said about this model. It's a cartoon. Of course, there's a huge number of important effects which are not in this model. But the model needs to only be good enough so that when we do inference, we get the right answer. Because our goal is not to, compress pictures of the sky or generate believable pictures of the sky. So the density isn't important. It's just that the posterior mode should be in the right place.
And a similar question, the addition of things that were not in your model, the first term.
Yeah.
Is it reasonable to assume that things are uniform, or maybe it's...
Sure. Again, you could say that maybe if there's some spatial effect, like near the outside of your image, things are dimmer than... But again, all that's required here is that the evidence for the right posterior is much stronger than the evidence for everything else. So maybe you should define reasonable.
You look at you can look from your data. You look at the two images which are the same part, and you see location of missing stars from one to the other, and you see, for example, is it really uniform or the
Right,
distance
and of
to
course
other objects
of course the answer is no, it's not really uniform, but that is the same answer for every statistical model that has ever been built of any data in the world. There is no model you or me or any of our colleagues have ever built that's right. So when you tell me, oh, but you look at this and it's not uniform, I agree, yes, it's not uniform. And when I look at errors in models you build, they won't be Gaussian. And so
I agree.
So now, what is this discussion really about? The definition of a model isn't whether it's right or not. No models are right. The definition is whether it's useful, in my mind. Right? So, yeah, of course, this will not be uniform, and this will not be Poisson, and these errors will not be Gaussian, and everything. Okay. So, so this is now, I think, the real crux of the issue here. So we discretize this hypothesis space, and now if we assume a uniform, we assume that before we see the image, it could be anywhere on the sky. Okay? So I should define the set M a little bit more carefully here, but imagine that the set M is all of the matching hypotheses that are consistent with a rectangular image on the sky. So for example, I'm not going to consider a hypothesis where this red dot is a star that's here, and the dot right next to it is a star that's on the other side of the sky. So the set M is only the set which are consistent with some image, okay? In that set, if I assume that before you show me the image, I don't know where, it could be anywhere, that's also not true. It's very hard to take certain pictures of certain parts of the sky. There are many more telescopes, for example, in the northern hemisphere than in the southern hemisphere and so on, but let's not worry about that. Let's just assume it's uniform. So then the posterior is going to be proportional to the likelihood here. But unlike in many problems, we actually do care about the normalizer. We really care about the normalizer because we're not going to be able to enumerate over all hypotheses M. We're just going to have a heuristic which proposes hypotheses M, and for each one, you're going to try and approximate the posterior, and when the posterior looks really high, really close to 1, you're going to stop and say, that's the right answer. So we really need to be able to estimate, we need to be able to estimate the posterior. I'm not sure why, is it possible that the power isn't turned on there?
Yes.
Okay, maybe I can, it doesn't matter, I suppose. Okay, so how are we going to estimate this? This is in principle to sum over all possible explanations of the probability of the image given that explanation. And so here's the main trick. The main trick is we're going to break this sum into 3 terms. So remember, I'm trying to estimate this denominator, this thing at the bottom, and I'm going to break it into a sum of 3 terms. The first is the actual explanation M whose posterior I'm trying to compute. That's the thing that's going to be in the numerator. Okay? The second term is the sum over all hypotheses M prime, except for that first one whose posterior I'm trying to compute, which have the property that the number of image sources not explained by noise is at least Q. Or in the language of this picture, they have the property that the number of red circles with green circles exactly inside them, up to some tolerance, is at least Q. Okay? So you can explain any image you want by assuming all the stars are distractors, right? I can say, yes, your image of the sky, which looks nothing like this part of the catalog, was actually generated from this part of the catalog, and here's how. All of the stars that should be there got turned off with z equals 0, and all of the stars that are there got generated by the uniform model. That's one explanation. It has terrible likelihood, but it's a possible explanation, right? Okay. So I'm only going to consider, in the second part of the sum here, hypotheses where the number of z's that is 1 is at least q. And then I'm going to group all of the other hypotheses where the number of z's that's 1 is less than q into the third term.
You already tell us what q is.
Q is it's just some threshold. So for any choice of Q, it would be a different grouping of these terms. So say, in my case, Q is going to be 4. So I say, you have to explain at least 4 of the stars in the image using stars from the catalog. And if you don't, then you get put in the third part of the sum, and if you do, then you're in the second one. I see a lot of frowning here. Let me tell you where I'm going with this, and then maybe that will make it easier. Where I'm going with this, of course, is I'm just going to assume every element of the third sum is 0. So I'm just trying to come up with a grouping of the terms where it's safe to assume that a huge number of them contribute almost no probability. And in the typical images that we're working with, there's tens or maybe hundreds of extracted sources. And if you explain less than 4 of them using the catalog, then it means you're essentially explaining the entire image by noise. And so those terms are essentially going to contribute 0 probability. I must not have done a good job explaining this because everyone is looking confused.
How many terms do you tend to get in the first sum?
So in the first sum, we tend to get thousands of terms. And in the second sum, in the one that we're leaving out, well, we don't know, but it's many hundreds of millions.
That's why I was finding, so that's less than expected.
Right. Some people are still not happy with this. No, why? You don't even want to ask a question? It's that bad? Ian?
So a small image from a small telescope might have a small number from the catalog, a huge image from some large telescope might have a large number. You're not distinguishing.
We're not distinguishing at all. And you might say that for a large image from a large telescope, for computational efficiency, I should set that number to more than 4. But as long as I can run the calculation in a reasonable time, setting it to 4 doesn't hurt me. It just means maybe I'm doing more work than I need to. Okay. So here's the second thing I'm going to do. I'm going to assume that every element of the second term except the true matching has the same value. Okay, now that sounds kind of outrageous, right? But here's the intuition I'm going to give you. If I find 4 stars in the image that exactly match the positions of 4 stars somewhere in the catalog, but that's wrong, it's a totally incorrect match, then what does the rest of the distribution of stars look like? It looks essentially uniformly random. Okay? So that's like saying, if I just think of it in a simple case, if I just took a corner of the image and you found a pretty good match to the corner of the image, but wrong, and then except for that corner you looked at the rest of the image, what would you expect to see? You'd expect to see essentially random. There would be no relationship between where the catalog stars were and where the other stars were. So all of the terms there, except for the correct one, have the same value. Okay? And that value I'm going to call beta. So NQ is the number of terms there, and the value of every one of them that was a false match is going to be called beta. Okay? And then that's kind of all we need. So now the posterior is of any particular explanation is just the likelihood of that explanation divided by the likelihood plus this term plus this 0, which we ignore. Okay? Now, we haven't yet said whether this is the correct explanation or not. If this is the correct explanation, then this is sort of order 1. Okay? And if not, then this is of order beta. Now, either way, let's divide everything by this likelihood term now. And this is what the posterior looks like. So the key quantity here is the ratio of the false probability mass to the true probability mass. Okay? This thing here is the false probability mass. It's all of the mass that came from the incorrect explanations. And this thing here is the true probability mass. It's the probability mass of the explanation whose posterior we're trying to assess. Now, either the explanation we're trying to assess is the correct one, in which case this term will be much larger than these, or there is no correct term, in which case this term will be comparable to these terms. Or the correct term is buried somewhere in here. And those are the three possibilities. So this thing I can just bound very easily using the exponential. And so what was that bound? That was just this, right? Okay. And now I can compute the log posterior, an estimate of the log posterior as this ratio. Okay. So those are the steps that we go through. And this all may seem kind of savage to you, but the idea is to be able to compute something about the actual numerical value of this posterior without ever enumerating over anywhere close to all of the hypothesis space. So sampling is out. Exact computation through any kind of dynamic programming is out. And we need to know this not just up to a constant. We actually need to know it numerically because the software needs to be able to say, yes, I know where your image is, or no, I don't know where your image is. We can't just say, well, up to some constant, here's the log posterior. That's not good enough. Okay, so how do we actually do this? So for each potential match, we estimate this posterior using the quantity I gave you, and essentially this looks at the number of coincidences, the number of matches between the catalog and the image that we saw. So you can think of those as hits. Think of it as throwing darts, right? The red circles, which are the objects you extracted from your original image, they're like targets. And the green circles are darts that you throw from your catalog. And if you're in an incorrect place on the sky, the darts are thrown uniformly at random. And if you're in the correct part of the sky, the darts are thrown exactly at the targets with some Gaussian noise, except that some darts don't get thrown. Okay. And you just want to look at how many darts hit the targets. Okay, so that's the kind of interesting part from statistical point of view. But if you actually want to make this work, there's a part that has nothing to do with statistics, which is how are we going to decide which matchings we should consider, right? All I told you was for a particular hypothesis, how to get an estimate of what its posterior probability was, essentially a numerical guess at whether it was going to be right or not. Thank you. But I didn't tell you how to figure out which hypotheses to examine. So, sorry about this. It's very funny. Okay, one possibility you might think of is exhaustive search. That sounds slightly crazy, but it's maybe not as crazy as you think. We actually did consider lots of fancy computer science tricks in which we could try and do exhaustive search. Is it on, David? Okay, thanks. But it's not really feasible, right? The sky is just too big to do this. I can try and show you a little movie of how big this is well, maybe I'll show it after so as not to risk interrupting it. But the exhaustive search strategies that we tried didn't really work. So here's what we settled on. It's a classic idea from database and computer science areas. It's called an inverted index, or maybe just an index. I don't know. The term inverted is sort of, depending on the field you're in, they either use the term inverted or not, inverted file system or index. But the idea is very simple, right? The idea is that you define a set of features for any particular view or image, and then you make index or an inverse lookup table which tells you for each kind of feature which places on the sky have that feature. So think about it in the text domain. It's easier to think about it in the text domain. When you go to Google and you type Bayes' theorem, how does Google decide which documents contain the words Bayes' theorem in order to rank them and show you the top 10 results? So here's what Google doesn't do. They don't take their however many billion documents and go to the first one and say, does this contain Bayes? And does it also contain theorem? And then go to the second one and say, does this contain Bayes and also theorem and so on? No. What do? They have an inverted file system. They have a list for every word, and actually for lots of combinations of characters and stuff, all the documents that contain the word Bayes. They pre-compute that list. So they look up Bayes, and it gives them a huge list of all the documents that contain Bayes. They look up theorem. There's another list of documents that contain theorem. They intersect those. And by definition, the intersection is the set of all documents that contain both the word Bayes and the word theorem. And then after that, they can do whatever they want with those documents to score them. Okay, so that's the simple idea of inverted file system. Is that lookup trick clear to everyone? It's very simple, right? So we're just doing the same thing, but instead of with words, we're using geometric features, okay? So for each feature, for example, for this type of geometric feature, I just make a list of all the places on the sky where that feature appears. Okay. And then how do we do matching at test time? So when we see a new test image, we compute which features in the test image are present, and then we use the inverted index to look up. So I go to some place in the image, I locate a feature, and I ask my inverted index, hey, where on the sky do you know that that feature, something close to that exists? And it tells me, oh, here are the places. And then I go to the image, I get another feature, and I say, where does that exist? And it gives me some other places. And I keep doing this, and eventually I build up evidence for one particular location on the sky. Yeah, question?
Feature just any combination of 4 stars, or is there something?
Right, so the question is, what are the features? That's completely up to us as part of designing the heuristic. It has nothing to do with the computation of the posterior. And so this is an area where essentially there's no hard theoretical guidance. It's a very empirical question, which features work. And I'm not sure we've picked the best ones. Now, for any class of features that you might design, like there's several strategies you can use. David and I actually talked about this problem almost 3 years ago, and at that time we were talking about a strategy where you would pick some stars in the image. The simplest case is a pair of stars. Use that pair of stars to lay down a grid, and then think of whether the grid was occupied or not as a bit. So you'd convert the whole image into a bit string. Right? So that's a class of features, which is kind of like a bit string or Bloom filter. The class of features we're using here are patterns of 4 nearby stars, the relative geometric positions of 4 nearby stars. And there's other classes of features. You could use 3 stars, like triangles. You could use 5 stars. You could use... For each class of feature, you can do some theory about analyzing the performance. So for example, David did some analysis in the Bloom filter case of how you would expect the performance to go depending on the number of grid cells you used and the false positive and false negative rate and so on. So but in general, I think whether you use the grid or whether you use 4 stars or whatever, that's an empirical kind of a question. Okay, so we did settle on these 4 stars. So just a bit more on this. In simple domains like text, you can apply this inverted index directly. But here, the features are a bit more subtle. They have to be invariant to scale, rotation, and translation. Okay, because you don't know the scale or the rotation or the translation of the image. They have to be robust to some positional noise. And then they have to also be robust to the fact that stars might be added or removed from the image. So these are the features that we use. They're these quadruples of stars, or informally we call them quads. So here's how we construct them. We take 4 nearby stars in the image. We use the 2 furthest separated stars, so call those A and B, to define a coordinate system. So just imagine drawing a unit box which has the 0, 0 corner at A and the 1, 1 corner at B. And the remaining 2 stars, C and D, in that box form a 4-dimensional code. It's like a hash code, a geometric code. So if you think about this, you can see that it's invariant to translation and rotation and scale. So here's one way to think about it. There's 4 stars, and on the sphere, those have 8 degrees of freedom. And we'd like to get rid of translation, that's 2, rotation, that's a 3rd, and scale, so that's 4. So we should be left with 4 degrees of freedom in the end if it's translation, rotation, and scale invariant. And in fact, the coordinates of these 2 stars in that coordinate system are 4 numbers, so there's 4 degrees of freedom left.
How do you know whether A and B are?
Good question. So Carl asks, how do we know about A and B? So we don't. And the answer is the code is degenerate. If you swap A and B, then it's like taking 1 minus everything in the code. And you can also swap C and D, right? Because there's nothing to say which should be C and which should be D, and that's like reversing the. So what we do is we arbitrarily put one of these in the inverted index, and then at test time we check all the combinations. So we just overload the hash function essentially. So that's right. Swapping A and B or swapping C and D doesn't change the shape, but it does sort of change the code, reflects it or swaps it, and so there's some degeneracy. Okay. Yeah.
How do you choose which 4 stars to use for that system?
Right, good. So the question is, how do we choose which 4 stars to use? And again, the answer is that this is somewhat heuristic, but what we do is at various scales, we just trim the catalog down so that the inter-star distance is about that scale. And then we build all possible 4 tuples of stars at that scale. So for example, we might say at the scale 1 arc minute. So at the scale of 1 arc minute, we just draw a circle of size 1 arc minute, and we pass it over the entire catalog, and every possible group of 4 stars that fits in a circle of 1 arc minute, we load a code. And then we double it to 2 arc minutes. So we get rid of some of the stars to make the interstar spacing about 2 arc minutes, and we take a new circle, we do it again, and 8, and so on. So we have many different codes at many different scales, and we keep them in separate files for reasons of having them swapped in and out on disk, because it's never possible for you to simultaneously consider the hypothesis that part of the image is at one scale and another part of the image is at a very different scale. There just aren't telescopes like that. So. Okay, so you can think of these as kind of continuous or vector-valued hash codes. And it is, in fact, it's robust to these invariants, scale, translation, and rotation. It also has the nice property that, except for this degeneracy, if stars are uniformly distributed on the sky, then the codes will be uniformly distributed in that quadrant of code space. So it kind of has Jacobian 0, or Jacobian 1, if you want to think about it that way. Okay. So actually, Ian Murray pointed this out. You might not know this, but basically a very similar trick is already being used by color photocopiers and Photoshop software. So there's this thing called the Urian constellation, which I didn't know about. You guys might know about. So a lot of money, including British pounds, American dollars, and some versions of the euro, have this pattern of 5 yellow dots. This pattern of 5 yellow dots, which watermark the bill. So they're there so that color photocopiers can decline to photocopy your money. So it looks like this. And on the American $20 bill, it's composed of the zeros of the number 20. And it also appears on the British pounds and so on. So if you've ever tried putting a bill on a color photocopier, it doesn't work. And this is the trick that's being used. So, okay, so here's the summary of the inference strategy. First, we identify objects in the image. So we take the image, we do this pre-processing to find locations of objects, and then we throw away all of the image and we just work with the locations of those objects. We cycle through all possible quadruples of stars in the image, using the brightest ones first, but that's just to schedule a computation. We don't use the brightness at all in the calculation. And we compute their corresponding codes. We look up the codes in this inverted index. The data structure we actually use is a KD tree because it's a low-dimensional space. We find matches within some tolerance, and then for each of those we estimate the posterior. And when the posterior gets close to 1, then we return and we say we think we found the answer. Okay, so our system is actually on the web, and I'm going to try and give you a demo of it now. I guess seeing is believing. So in principle, what you do is you just get your image, you upload it to this website, and we give you the answer. And so this is, I think that it's interesting to try and push these pattern recognition problems into this regime where there's no discussion about reproducibility. The output of your research is a website. And then nobody has to argue with you about whether they do or don't believe your experiments. They can just go to your website and do whatever experiments they want. So let me try and show you this demo here. So there's something called the astronomy picture of the day. And the nice thing about that is that we don't run it. It's run by NASA. So you can't accuse me of cooking the images to make them easy, right? So this is the astronomy picture of the day today. Unfortunately, it's not a picture. It's not a picture of the sky. So let's go to the archives and find some nebula or something. Oh, now you're getting suspicious, right? Okay. I don't control it. We can do more examples if you want later. Here's the, I'm just going to copy this image location, and then I'm going to go to, so this is just running on someone's workstation at NYU. Okay, and I'm going to paste the URL in here and submit it. So what is it going to do? It's going to go to this website. It's going to download this image here, and it's going to run the simple computer vision algorithm on the image to extract the stars. So it's downloaded the image, it's extracted the sources, and then when we hit this button, it's going to submit that list of red dots, and it's going to try and solve it. And it's going to solve it when I hit the button. It's not pre-solved. It's not solving it now. It's not so. So you should notice in this that, for example, there's a lot of junk here. Like there's this weird cloud, which isn't really a star, and it's put a dot in the middle of it. And there's some stars in other parts of the image which aren't detected, but that's OK. So I'm going to hit this button to submit it. So now it's searching, and now it's found it on the sky. So the search time is generally less than a second. And here it is. It tells you exactly where your image is, the RA index. It gives you this plot, which shows you which parts of the image were explained by the catalog and which parts were explained by things that weren't known in the catalog. It shows you the quad that was the first quad that led it to that hypothesis. And then it annotates your image. It tells you which things are in your image. It tells you the informal name for them and the NGC number, and we can do all kinds of other things about the image. Okay, so this is really the goal that we set out at the beginning. You start with just the pixels, and you end up with basically everything that is knowable about the image now could be known, because we know exactly where it is. And so if we want to do a lot of work, we could figure out all kinds of things like the telescope distortion and the point spread function and all kinds of things like this. So let me go back to the slides and show you some more examples. So this is an amateur shot by an amazing amateur called Jerry Rodriguez. So he takes many, many exposures and stacks them and does false color. So a lot of this is not physically real. Most of the colors here are just created by him in Photoshop. But that's OK. We detect some stars, and we match to the catalog, and we label it. And this is 1.5 degrees on the side. Here's another. This is another astronomy picture of the day. So this is taken with a tripod in the Utah desert. So it's a digital camera. It's a consumer-grade digital camera. It's not a telescope. And we detect some stars, but not very many. And notice that now we're detecting things on the horizon incorrectly as stars. These are houses with little lights on them, so we detected those as stars. And this is a lake, and we detected the rim of the lake. So that's all fine, right?
Not a UFO.
Yeah, it's not a UFO. And so this is a 57-degree image, so it's very, very wide. There's lots of distortion in this image, and we can mark the constellations, of course, and everything. Here's an image from the Sloan survey. So that's half a degree, much smaller. This is actually David. When David gave a talk about this image was an example on his first slide. And then my graduate student was like, ooh, let's try and solve the image in David's talk from 2005. So he went to David's slides, and he grabbed the image, and he uploaded it into the system. And of course, so that was the one that I started with. Here's a scan of a historical plate. So this is from the Harvard archive. They have thousands, maybe 80,000 glass plates that they're scanning. And so this is one of the interesting applications, is to annotate these plates correctly. The only information about where these plates are is in the corner there's a number written in grease pencil. You can see it if you look. It's actually flipped. And they have to look up that number in a card catalog. And then that references a logbook, and then they read the logbook about where it is. So it's a very complicated process right now. Okay, another amateur shot. Oops, you wanted me to go back?
Yeah, one more. Yeah, it's a double image. It's got the same as in the middle and at the bottom. Go back one more.
It could very well be double exposed.
So you see there's a quad bang in the middle and a quad down at the bottom. They're the same.
So sorry, where are you?
So bang in the middle, but 100
Yeah.
to the left, there's a quad that is
Yeah.
and the same type is exactly reproduced.
Yes,
down the
it's
bottom.
quite possible that it's a double exposure. If you look at the top, that square might be the same one. It's quite possible. So we could look maybe at the catalog and try and figure out if that's true.
Yeah, so there's all those red things down at the bottom that aren't explained
Right.
because it's a double exposure.
Yeah, that's quite possible. Okay, let me go. Oh, here's an example of occlusion. So the system doesn't know about the moon, of course, so there should be all of these stars behind the moon. But of course, they're not there in the image, but it doesn't matter. It's still perfectly fine. Okay. So let me just tell you a few results about scaling up. So we did some tests on the Sloan Digital Sky Survey. So this is a huge number of images, all from the same telescope. We ran about 300,000 images and compared it with the image data that the Sloan pipeline writes out. So we got 0 false positives. We got about 99.9% of them, 99.8 solved. So 530 of them didn't solve. And of those 530, something like half are errors in the Sloan survey. So they're software errors in the pipeline or bad exposures or something like that. And the other half are false negatives, which is fine. We have to have some false negative, right? And almost all of them solve only looking at the 60 brightest objects. So when you look at a Sloan image, it has hundreds of stars, but if you just order them by some arbitrary measure of brightness and only look at the first 50 or 60, you can solve almost all the images. These are some scaling up results, which I won't tell you about yet, about the speed, but I want to tell you about something interesting. So here's some preliminary results about finding the date of an image. So John Barron is the graduate student who did this work, and he came up with the cute name blind date. That maybe is only funny if you're American. But so the idea is take an image and say what the date of the image is. So these are, we used historical images so that we could get a range of dates. So these are pretty good historical images, science quality images. And the dates range over about 50 years, and the mean error in estimating the date is only about a year and a half. So here's the various 27 images. This is the year that they were taken. The X is the true year, and the circle, the O, is our estimated year, and the gray are the error bars that we produce. So how do we do this? Well, there's a very small number of stars which move on the sky. And so we take those stars and we run the clock forwards and backwards, and we ask, what setting of the clock, according to what the astronomers know about how these stars move, best explains the image that we have? Once you know where the image is, then you can do this sub-pixel localization and run the clock forward and backward and find the best. So now we're able to also estimate within a year or two the date. Here's some poorer images. These are low quality images, and still, with the exception of a couple of outliers, also very good results within 4 years on low quality images. Okay, so just let me finish off by saying that I think that there's a lot of other areas in which inference is a very interesting tool for scientific data analysis, even when the learning problem is essentially trivial. So where there's a very strong physics that tells you what the model is, and all the action is in inference, and inference does some kind of explanation for you where you really believe that there's a kind of single underlying explanation that makes sense. So I've worked on other problems here. One is automatic alignment of curves. So if you have a repeated experiment which generates some kind of experimental trace, but there's time variability and amplitude variability, and you'd like to just average the curves together. Sensor calibration, where you have different exposures, and I've also done some work on timescale modification of speech and audio. So if you're interested in any of those topics, I would be happy to discuss more about that with you. But I think that we shouldn't forget about the regime where the model is essentially known and inference is where all the action is. Okay, so these are the two amazing graduate students, Keir and Dustin, who built the huge amount of engineering underneath. This is John, who's been working on problems in date and bandpass estimation. These are the two astronomers, David and Michael at NYU. And the website is up at astrometry.net. That's the word astronomers use for the location of an image on the sky. So you can check it out, and all the code is open source. You can download it and compile it yourself if you'd like to give it a go. So thanks a lot. Questions? Gripes? Carl?
So what's the computational time to set up the system?
Right. So the test time is very fast. So let's go to some of these scaling results. It takes us about a week to build the inverted index, and that takes only like maybe 400 gigabytes of disk. So if you bought a good workstation with a big disk, you could build it all yourself. The real issue is that once you build the indices, they occupy something like 100 gigabytes, and you'd like to have them all in RAM if you don't want to do a disk seek when you solve. So these times are predicated on having enough computers that you can have about 100 gigabytes of RAM. So depending on how rich you are, that's something between 3 and 20 computers. And so if you have sort of 80 gigabytes or 100 gigabytes of RAM's worth of computers, then you can get the solve time down to hundreds of milliseconds. So here's a result which tells you on the Sloan survey, this is the average amortized CPU time per field. And it's almost all dominated by CPU time. So once you load the indices into memory at the beginning, this is pretty close to wall clock time. And this is in milliseconds, so 10 milliseconds, 30, 100, and 1 second is up here. And this is the fraction of the fields you can solve if you give yourself that much time. So if you're only willing to spend 100 milliseconds, you can still solve 95% of the fields. So the take-home message is all the work is in a small number of very, very hard images, which are tough to solve. So yeah, that's the. So in some sense, it's kind of lucky, right, that we just managed to squeeze the system into what you can do on a relatively affordable computer today. David, and then Peter.
You're wasting a lot of computer time in those cases and disk space with a whole load of hypotheses that shouldn't be thought about at all because they involve stars of completely different brightness from each
Yes,
other.
definitely.
Could you shrink it down by another factor of 20 by?
I don't have a good estimate of how much you could save. But so David's question is, aren't you losing a lot of potential efficiency by not looking at the brightnesses at all, except in this very weak way to just schedule which things you check first? Or to put it another way, it would be extremely unusual for there to simultaneously be a very dim star viewable in your image and a much brighter star in the same bandpass that isn't viewable, where there's just nothing there in your image. That's essentially impossible under any reasonable telescope model, but you guys consider that and millions of hypotheses like it. So that's totally fair. We just haven't found a way to incorporate brightness because brightness is a sort of meaningless unit. Unlike position, where for most pictures, position is, you can believe your position up to, within half a pixel. Brightness, you have no idea what intensity units in your image mean in correspondence with any physical brightness because there's so many mostly monotonic but not always monotonic transformations in between the photons and the ink.
Yeah, I'm not imagining using the brightnesses in the image so much as when you're creating your index with all the conceivable hypotheses in it.
Oh.
Your index includes a whole
So
lot of
that we do a
hypotheses.
little bit of, because when we cut, when we thin our index to make the interstar spacing at scale alpha, we do that thinning by dropping the dimmer stars first. For some arbitrary definition of dim, mind you, right? Because you could say, well, dim in the red or dim in the blue, or, but. So we do a little bit of that, yeah.
Yeah, I guess two things. One is sort of simple. I mean, you're presumably, for many of these pictures, can get information other than simply the pixels, right? I mean, say the amateur astronomer can type
Sure.
in, you know,
Sure.
So that information, presumably, you
Right.
some way of using.
Right. I'm trying to see if there's one. There's some images where they actually say on the image, in the image itself, where the image is, but none of these. So, yeah. So we haven't used that, and the reason is we don't really need it in the sense that we would like to be able to solve it without that. So we had to build the system to work, and the system works well enough that there's no obvious way to incorporate it. Now, we could have a fallback system where if you can't solve the image, then we come to you and we say, could you give us a hint? You know, could you type a keyword of an object that it contains or tell us the scale or the model of the telescope that you use or anything? And then we can narrow the search.
Okay. The other thing is this inverse index notion.
Right.
Described as a computer science notion, but it also can be thought of statistically, right? I mean, you imagine that somebody draws a patch from the sky, uniformly from the sky, and
Right.
then on that crude observation, you can compute these various features, so
Yeah.
random variables, and then you go, basically what your index tells you is sort of what the events are. You know, you have your...
Sure.
But now, couldn't you use...
It's hashing or sketching if you want.
But couldn't you also use sort of crudely, for example, probabilities, right? I mean, in the sense that you look at this feature and it really is much more probable, so to speak, that it comes from this part of the sky than from that part of the sky.
That's right.
And then you could cut things down somewhat.
You could do that. There's a continuum between features which are in isolation not very informative, but whose conjunction is informative, and features which are in isolation extremely informative. Okay, so we're kind of on the side where each feature is not extremely informative. Or to put it another way, each time we find one of these codes, when we look it up, we get something like 3,000 or 4,000 possibilities. Okay. We could move to a regime where essentially as soon as you find a feature, there's only 3 or 4 places on the sky. But the problem with that is those features have to be there have to be many more of them, right? If you think about the feature has to communicate mutual information about the image, well, so then we would have to have exponentially more features. And then it just becomes a hassle to build the lookup table.
Yeah, but you could, I mean, in a way you could view it as a design problem. I mean, you could then ask, you know,
Definitely.
Are there combinations of variables which
Yeah, that's absolutely true. And in fact, it's almost certainly the case that at the bigger scales, we should be using features like triangles instead of quads, because at the bigger scales, everything is so easy and you don't need very informative features. I agree. It's a very interesting, it's like there's an optimal basis of some kind that we haven't explored at all. Anyway, I'm over time, so I'll let people go. Thanks again for coming, and please come up if you want to try out the system or go to the website and download it.
You have to be over time, by the way.
Oh, I don't?
There's nobody else coming in.
Oh, well. yeah.
More questions.
Right. Oh, right. Sorry. If there are more questions, I'm happy to take them. Oh, and shall we, just so people don't think that I'm trying to slither out of things, shall we go here and have somebody else pick from the menu of somebody? Carl, when is your birthday?
1809, 69.
Well, you don't need to tell me the year. So September 18th? September 18th.
Said you had a movie as well to show.
Oh, I have a movie to show you, yes. Whoa, maybe. I don't know. Okay, we'll give it a go. It's going to be tough, but we'll try that. Ooh, okay. So while that is while that's going, let's see if I can find the movie. Okay, I don't know. There's not a whole lot of stars in this image. Ooh. Most of them aren't stars. Most of them are lava flows. So I think it's basically hopeless, but let's give it a try. Now, of course, this is going to take ages because when it doesn't solve, it takes ages. So while that's taking ages, not solving, let me see if I can find this movie for you. Good. Here it is. Okay. So what is this? This is a movie which starts at the scale of a Sloan image and zooms out to the scale of the whole sky. So keep your eye on the red box if you can see the red box. And okay, it's looking a little bit daunting. Okay, so this is sort of the visualization of why exhaustive search is just not on. D?
What do you do with the images that people upload?
The images that people upload? So currently we have a checkbox in which you can say whether you would like your image to be publicly viewable or not. And if you check it, then we just have a little gallery page where people can look, and if not, then we don't. But when we put the system up for public use, we're thinking of requiring that you make your image publicly available as a condition of us solving the image, because otherwise it's not clear that, I mean, the goal here is to create essentially an open source survey of the sky, and it won't work if people just use it to annotate their private images, but their private images stay on disk. Now, of course, they can always download the source code and run the installation themselves. So,
is there any facility for them to say, yeah, you got it right, or you didn't get it right?
there is, in the alpha testing program, if an image incorrectly solves, they can send us an email, and there's a web form they can fill out to indicate that. But we've found that almost all the false positives have either been errors on the part of the photographer or errors in the catalog. So there's some extremely amusing parts of the USNOB catalog. So what's a typical false positive? A false positive is like someone uploads an image of like New York City, and there's a sign in Times Square with a line of lights, and it detects a big line of lights. And then somewhere in the US Naval Observatory catalog, that one of the scanned plates got scanned on its edge, and the scanner detected all these stars on the edge, and those stars got loaded into the definitive catalog of stars on the sky. And then the system said, oh my God, it's amazing. There's a line of exactly 40 stars in your image and the same line of 40 stars in the catalog. It must be the right place. Okay. In fact, if you go looking in the USNO catalog, you can see all kinds of things. You can see these lines. You can see numbers written by hand in the catalog, which represent, people who wrote on the plates and then the plates got scanned and stuff. So there's a lot of errors in the data, which, now, under the simple model, right, that explanation does have very high posterior. But yes, there is a facility for that. Part of the problem is that it's essentially impossible to scale this up from an academic environment, because otherwise people just spend their whole lives rebooting Apache servers and stuff, and that's, my graduate students have been amazing at doing that, but that's not what they should be doing. So. Let's go see if Carl's birthday solved, which I don't think it did. No, it hasn't solved.
Do another.
Anyway, do another one.
Do
Okay.
the day after.
Do the day after Carl's birthday. Okay. So September 19th, September 20th. Ooh, this looks promising. Okay. Copy image location. Ooh, we might be in for a bit of trouble here if the other job is still running, but we'll see. The fan on this workstation is just turned on. Okay, that looks like something much more reasonable might happen. There it goes. So there it is. Oh, I guess the drawing code for the constellation is a bit wacky, but anyway, you can certainly see. So that image is, it contains part of the constellation Cygnus and all of these other things. But if we look at the title of it, it says Northern Cygnus. So that's some confirmation that, that it's actually correct. And this is the, it's 13 by 10 degrees wide, which is pretty believable for an amateur-sized image. So. Okay, thanks again.